All right, let's get right into this explainer on the physical barriers and engineering architectures for our future interstellar missions. For decades, we've all looked up at the stars and wanted to go there, right? But translating those dreams into actual, viable engineering means confronting some pretty brutal realities. Today, we're looking strictly at the numbers, the physics, and the modern architectural models that we, as space agency engineers, have to use to map out our first true steps into the interstellar void. And to really plan these missions, we have to grasp that the universe isn't just vast, it's actively restrictive. Physicist Leonard Susskind hit the nail on the head when he said, "The universe is not an ocean, it is a cage. We can't just build a bigger boat to sail across it. The bars of this cage are forged from energy, mass, and a universal speed limit that fundamentally resents our ambition." So here's our agenda for the explainer today. 1. The interstellar physics barrier. 2. Legacy and theoretical architectures. 3. Subluminal warp drive modeling. 4. Nanocrafts and directed energy. 5. The TARS architecture mechanics. And 6. TARS orbital and material dynamics. Let's kick things off with Section 1, the interstellar physics barrier. Before we even think about engines, we have to look at what the universe does to a ship when it tries to move at extreme speeds. Speed creates this vicious, fatal loop. Thanks to mass-energy equivalence, E equals mc squared, the energy you pump into a ship to accelerate it actually adds to its inertial mass, making it harder and harder to push. Plus, the environment itself gets insanely hostile. Above half the speed of light, sparse interstellar hydrogen turns into lethal radiation that'll shred electronics and passengers. In that harmless cosmic microwave background from the Big Bang, it Doppler blue shifts into a brutal wall of high-energy radiation drag. Trying to go fast literally weaponizes the cosmos against your spacecraft. To put that mass penalty trap into perspective, look at this. At 99.9% the speed of light, your ship behaves as if it's 22 times more massive than it was on the launch pad. It's an inescapable loop. The heavier it gets, the more energy you need to squeeze out just a microscopic fraction more speed. It makes hitting the speed of light practically impossible, regardless of how perfect your fuel is. Moving on to Section 2, Legacy and Theoretical Architectures. Engineers have pitched some incredible brute force ideas over the years to bust out of our solar system. Think back to early models like nuclear pulse propulsion, famously studied under Project Orion, or hybrid fission sails. The idea there is simple: detonate nuclear materials to push the craft forward. But the mass penalties are huge. You have to carry all that heavy onboard fuel, and since these engines run unbelievably hot, you need giant thermal radiators. We're talking square kilometers of liquid droplet radiators just to stop the ship from melting into slag. Then you have self-fueling concepts like the Bussard Ramjet. The thought was, hey, let's just use a giant magnetic field to scoop up that interstellar hydrogen for our fusion engine. Sounds great, right? No heavy tanks. But recent math shows that very same magnetic field creates immense drag against the hydrogen. Throw in the heavy physical shielding you absolutely need to survive your own fusion radiation, and your theoretical speed is effectively capped around just 10 to 20% the speed of light. All right, Section 3, Subluminal Warp Drive Modeling. Let's completely ditch conventional rockets for a second and talk warp drives. For decades, the Alcubierre model was the gold standard, compressing space in front of you and expanding it behind you. The math works, but here's the catch. It requires negative energy, an exotic substance that doesn't actually exist in nature. But lately, there's been a real game changer. Modern research is trading that unphysical model for a positive energy subluminal warp drive. By using a stable shell of regular matter, you can maintain a warp bubble at constant subluminal speeds without breaking the laws of physics, and zero exotic negative energy is required. And this isn't just whiteboard theory anymore. Space agency engineers and researchers are using open-source numerical tools like Warp Factory to actually build 3D models of these metric scalars. By looking at these surface plots, they can calculate the exact positive energy density needed to sustain a subluminal warp bubble. You can see how thickening the wall of the warp bubble drastically lowers the required energy density. Now, it still requires an astronomical amount of mass, but for the very first time, it's rooted in known physical energy constraints. Next up, Section 4, Nanocraft and Directed Energy. Warp drives are fascinating theoretical models, but let's look at a much more near-term, practical paradigm, the light sail. By abandoning onboard fuel entirely, light-powered nanocrafts completely cheat the rocket equation. Early mid-20th century designs struggled because they just couldn't scale up their massive refractive areas without getting way too heavy to push. But today, advances in materials science give us nanometer-thick photonic crystal materials. We're talking about gram-scale microprobes riding on highly reflective sails that could theoretically hit 20% the speed of light. But how do we actually push them? When we evaluate the engineering trade-offs, directed energy systems, like the Breakthrough Starshot initiative, rely on staggering infrastructure. Imagine trying to build a kilometer-wide, 100-gigawatt ground-based laser array, and then somehow dealing with the insane thermal heat so you don't instantly vaporize your own sail. That kind of astronomical cost and complexity is exactly why our focus is pivoting to evaluate purely solar-driven models instead. Which perfectly leads us into Section 5, the TARS architecture mechanics. Enter TARS, or the Torqued Accelerator using radiation from the sun. It's a super elegant, low-cost solution that entirely skips the need for gigawatt lasers. Instead of trying to get a straight radial push from a laser or the sun, which drops off incredibly fast as you move away, TARS acts like a massive flywheel in space. It just gradually stores incoming natural solar energy as rotational kinetic energy. So how does the whole shebang work? Picture a tether with two paddles. One side is highly reflective, the other side absorbs light. Because of those contrasting albedos, the asymmetric solar radiation generates a constant torque. Over weeks or months, the whole structure just spins up in the sunlight, rotating faster and faster. Then, right before the tether reaches its absolute breakup tension, it lets go. It releases the microprobe payload tangentially, slinging it out at incredible interstellar velocities. And finally, Section 6, TARS orbital and material dynamics. Of course, for TARS to work, we have to carefully balance the orbital dynamics. Normally, the outward push of the sun ruins traditional solar sails by blowing them away into weaker sunlight, but TARS leverages the quasi-Kepler effect. Essentially, the solar radiation pressure pushes back just enough to counter the solar gravity acting on the craft. This lets the probe hold a stable sub-Keplerian orbit. It safely trails behind the Earth, locked deep in solar proximity, just continuously soaking up intense sunlight while it charges. Then we have the tether material, arguably our most critical component. Graphene is an absolute beast, offering 130 gigapascals of tensile strengths. But good luck mass-producing it in large continuous sheets right now. So carbon nanotubes, or CNTs, step up as our mature, ready-to-go baseline. At 20 gigapascals, they are commercially available and more than strong enough to handle the extreme centrifugal forces for these missions. And here is where orbital dynamics really brings it all home. By dropping the CNT-tethered TARS deep into a solar orbit, much like the Parker Solar Probe, and exploiting the Oberth effect at perihelion, we can literally cut the critical velocity needed to escape the solar system in half, down to about 6 kilometers per second. By combining mature carbon nanotubes with precise orbital mechanics, we can successfully fling a smartphone-sized payload out into the interstellar void using absolutely nothing but the natural light of the sun. So as you evaluate all these architectures we've discussed today, from the massive energy hurdles of warp drives to the immense infrastructure of directed energy laser arrays, consider this. Our ultimate departure from this solar system isn't going to be powered by sheer brute force fighting against the cage of relativistic physics. It will be achieved by the elegant, precise mastery of light and material tension. What new material science breakthrough will finally allow us to spin up, detach, and step out into the wider universe? That is the real question driving the next generation of interstellar engineering.